Woo. Welcome back to section 2.4, measures of variation. So to think back, what have we done thus far in chapter 2? Well, we've talked about how we display data, right? We've talked about how we display, how do we show people what we have learned. They're not really what we've learned, but show people the results of a certain study, right? That's really what we've seen here. We talked about it in terms of all the data, basically frequency distributions and dot plots and stem and leaf plots. We talked about how to think about the center of the data, which was section 2.3, the measures of center, the mean, the median, the mode, things like that. And now what we're going to talk about are measures of variation, because it's not only important to talk about where the center of the data lies, but also how does it change? How does it vary? How does it deviate away from that center? That's what we're going to be looking at in section 2.4. How do we talk about that, right? How do we talk about how spread apart the data really is? That's measures of variation, okay? That's the lesson for today. So the first measure of variation we have, I think we talked about it already, but the range. The range of a data set is the difference between the maximum and the minimum. Finding the range of the test grades. Obviously, I would just take the biggest number minus the smallest number in this case. So the biggest would be a 90. Oops, that's not a 10. The biggest would be a 90. The smallest, excuse me. Biggest would be a 93. Right? Is any a bigger one? Nope. Biggest would be a 93. Smallest looks like it would be a 63. So therefore, I have a 30-point spread in the data, right? That is a 30-point spread in the data. Oh, jeez, I didn't take the lowest one. Mr. Laverick, come on now. Use your eyeballs. 54 is my lowest. Didn't find the biggest, I didn't find the smallest. So minus 54. So 93 minus 54. There we go. 39. 39 point spread, right? Okay, good. So it's a 39-point spread. And if I increase the range, obviously that increases the distance between the highest and the lowest amount. That's a measure of how spread apart the data is, right? We can talk about where the center of the data lies. We can talk about outliers of that. But really what the spread of the data shows you is how far it deviates away, right? The range doesn't really tell you where the middle was. It just tells you where the two endpoints were, right? That's the range. Now, when I talk about deviation, our definition of deviation is going to be the deviation of an entry X in a population data set is the difference between the entry and the mean. The difference between that entry and the mean, mu, of the data set. Now, that implies, there should be a little X bar here, that implies that each piece has its own deviation, right? I am saying a deviation of a specific data entry, the deviation of an entry X within a population or sample, the deviation of an entry X in a population or a sample is the difference between that entry and the mean. Whether you're talking about the population or the sample, it's that X value minus the mean. So deviation of a population data set would be X minus mu. Deviation of a sample would be X minus X bar. Okay, that's the distance away, basically. How far away is that entry deviating away from the center? That's deviation. Okay, deviation. That's how far that piece is pushed away from the center. Okay, find the deviation for each starting salary of these 5 new hires. I have to look at my notes real quick. I know I've changed an example in here. Just want to make sure that I use that. And the deviation. Okay, yeah. I think I'm good here. Okay, so the first thing, to find deviation. So it looks like I've got 5 new hires. The first thing I need to do to figure out what deviation is to find the mean, to find the X bar, right? So in this case, I need to figure out what that is. 47,896 plus 53,163 plus 48,322 plus 57,892 plus 56,462. I better double check that. 47,896, 53,163, 48,322, 57,892, 56,462. Okay. And then I'm going to divide that by, looks like I've got 5 new hires. So therefore, 52,747. 52 X bar is 52,747. That's our mean of these 5 people. Okay, now to find the deviation for each entry, I am just going to take each entry. So I'm going to make a column for X. I'm going to take each entry, and then I'm going to take X minus X bar, right? And that column will be the deviation. So let me set this up real quick. 47,896, 53,163, 48,322, 57,892, 56,462. And I'm going to find the difference, the difference between each one of those entries and the actual mean. Okay, so 47,892 minus, well, I'll put this in. 52,747. And that's going to be negative 4855. Negative 4855. Okay, we'll do that exact same thing, but now I'm going to put in 53,163. 416. Do the exact same thing, but now I'm going to put in 48,322. Negative 4425. Same thing, but now I have 57,892. 5145. Same thing, except now I've got 56,462. 3715. Okay, now those are my deviations, right? Those are my deviations. What can we tell from deviation? We can tell, well, whether it's positive or negative, whether it was lying above the mean or below the mean. Any negative deviations would have lied below the mean. Any positive deviations would have lied above the mean. The closer you get towards 0 for the deviation, the closer that value was to the mean, right? We can tell certain things by its deviation, right? The bigger the value of the deviation, the further spread apart it was, okay? If I added up all of these X minus X bars, what would I get? What do you think I would get? What do you think I would get? Probably 0, right? Because if I want to say, okay, these deviations represent how far spread apart, let's see. Negative 4855 plus 416 plus negative 4425 plus 5145 plus 3715. I get close to 0. Why didn't I get actual 0? Did I screw up on a... I think you should get actual 0. Negative 4425, 416, 4855. Well, you should get 0. Don't tell me. Or something really close to 0. Looks like I probably just messed up on a number here or there. All right, but that's deviation. Okay, now let's talk about variance. Let's talk about variance. Population variance of a population data set of n entries is, now this is where it starts to get a little funky. This is where your formula sheet comes in handy. This is where we start talking about population variance and population standard deviation. Okay, yeah. We're going to do these a lot of times, and it's almost like you're going to memorize them just by doing them so many times. But again, you don't need to memorize them. You will have them on your formula sheets. Okay, let's talk about variance. Variance. Now, this symbol here, okay, that symbol, another Greek letter, that's the Greek letter sigma. Oh, wait, you said sigma was that capital E. Yeah, that's lowercase sigma. Okay, that's lowercase sigma. Sigma squared, that's just how we talk about variance. That's just the notation for variance. Sigma squared is equivalent to the sum of, sigma again, sigma of the sum of x minus mu squareds divided by n. So what is that really? That is your your deviation squared. You add them all up, you divide it by n. So this is implying that you will get one variance for the entire data set. You will get a variance number for the entire data set. The sum of your x minus mu squareds divided by n. That is your variance of the data set. Where each number had its own deviation, the data set has its own variance. Okay? So x minus mu squared divided by n. The sum of your x minus mu squareds divided by n. Now, when I solve for just sigma, obviously I would be square rooting the opposite side. When you square root the opposite side, it turns from variance into standard deviation. Now, I've got to be completely honest, 100% clarity here. We hardly ever talk about variance. We hardly ever use variance. Is it a thing? Yes. Could you use it? Yes. But standard deviation tells us a lot more. So, and you really kind of solve for variance when you do standard deviation, because you just take the square root of the variance and boom, there's your standard deviation. But again, standard deviation is used so much more commonly, so much more often than variance. Okay? So again, we're going to talk about standard deviation rather than variance a lot of the time. Now, does that mean we'll never talk about variance? No. Sitting in front row. Or such as hair. I know Mrs. Apple. She won't stand for that. She sees that thing, she'll rip that out of the. All right, so standard deviation. Sum of the x minus mu squareds divided by n, and then we just square root that thing. Okay, some things about variance and standard deviation. You know how just regular deviation it could be positive or negative. I said if it was negative, it was below. If it was positive, it was above the mean. When we talk about variance and standard deviation, it is never negative. It is always positive. Why is that the case? Well, because we've squared this thing, right? We've squared that thing. Now, side note to that, be careful when you run the numbers and you find the sigma of x minus mu squareds, you kind of have to treat it like this. Okay? Be careful. You're not going to take x minus mu, add them all up, then square. No. You're going to take x minus mu squared for each individual one, then add all of that up. We'll do that here in a second, but just be careful with that. You got to kind of understand the notation, what's going on. You got to take x minus mu squared for each individual entry, add those all up, divided by n, and then we square root to get our standard deviation. Some things about standard deviation. Standard deviation is just a measurement of the variation of the data set. Okay, and it's a measurement of how far the data is away from the mean, right? How far spread apart the data is from the mean has the same units of measure as the data set. So if I'm talking about a test grade, the standard deviation is also like the points, right? If I'm talking about temperature, the standard deviation is also temperature, has the same units of measure as the data set. Standard deviation is always greater than or equal to 0. It's always positive. If the standard deviation comes out to be exactly 0, well, then you have a perfectly aligned data set, right? Standard deviation equals 0. The data set has no variation at all, and all entries are the same value. Like if I said, okay, I took everybody's, I don't know, how many, I don't even want to say it. If everybody came out to be the same value of 2 or something like that, well then, yeah, it's all the same data entry, that would have a standard deviation of 2. As the entries get further and further away from the mean, that is more spread apart, the value of the standard deviation is going to increase. So what can we tell from standard deviation? The bigger the standard deviation, the more spread apart the data is. The smaller the standard deviation in relation to the mean, then the closer that data set fits to the mean. Be careful. Don't just automatically assume that a standard deviation of 30 is more spread out than the standard deviation of 1. Be careful with that. If I'm talking about in terms of hundreds of thousands, and I say your standard deviation is 30, well, then that means those things are really close together. If I'm talking about the standard deviation is 1, but then my measurements are in like hundredths of an inch or something like that, well, then, yeah, it got pretty far spread out. It just depends on the units of measure. Okay, so let's take a look here. The ACT scores of Mr. Laverick's stats class are shown below. Find the population standard deviation and variance. This is not actual. This is just, made up information. The ACT scores of Mr. Laverick's stats class are shown. Find the population standard deviation and the variance. Okay, so what I need to do here is to create myself a table. You're going to be making a lot of tables. Got to keep yourself organized. You guys got to find the joy in the simplicity of these things. You got to find the joy in the monotony. Yeah. Monotony meaning like doing the same thing over and over again. You got to find the joy in the doing something over and over again. Yeah, that's the only way to find joy in these things. Okay, you just gotta be okay with being tedious for these things. All right. So first thing I'm going to do is list out my data. We got 22, we got 19, 18, 25, 28, 29, 30, 32, 26, and 29. Let me make sure I didn't miss any. 22, 19, 18, 25, 28, 29, 30, 32, 26, and 29. Okay, so this is my X. Next thing I'm going to do is find my mu. Right? I've got to figure out what my mean is of this data set to be able to find the standard deviation and the variance. Okay, so I've got 22 plus 19 plus 18 plus 25 plus 28 plus 29 plus 30 plus 32 plus 36. Oh, no, 26, excuse me. Got smarty pants on our hands. We got 36. 26 plus 29, right? Just double check. 22, 19, 18, 25, 28, 29, 30, 32, 26, 29. Add them together. Bingo. Divide by how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, that's nice. 25. Oops. Go 2. Divide by 10. 25.8. So mu is 25.8. Okay? Now, the next column that I'm going to make is x minus x minus mu squared. When I first started teaching this, I had you guys do like x minus mu, then x minus mu squared. Why? That's 2 columns that we don't need to show. Let's just do x minus mu squared. So that means that's going to be 22 minus 25.8. Actually, I should have put that in parentheses. 22 minus 25.8 squared. Okay, that's going to be my next column. X minus mu squared. 14.44. Okay, we got to run that 10 times. So I do the exact same thing. Come on, buddy. It'll be a long day if you do that. Say, put that back in. If you don't know how to do that, that's a very useful keystroke there. To be able to put that back in. Oh, wait, you guys can just up arrow now, can't you? Oh, that's nice. See, I can't do that with this thing. If I just hit up arrow, it just stops. If you hit second entry, it'll just bring back whatever you just used. So I'm going to say 19 here, 46.24. Do the same thing with 18, 60.84. Do the same thing with 25. Really small number here, 0.64. That number's so small. Why is 0.6? Why is that so small? In relation, this was giant, 46.2, 60. And then I go to 0.6. Why? It's close to the mean, right? That number was very, very, very close to the mean, 0.8 away. So it makes sense if it was only 0.8 away. It's 0.64, square 0.8. All right, you got 28. 28 gives me 4.84. We've got 29. One more unit up. 10.24. Again, find joy in the boring. I know I'm just punching numbers in my calculator. Trust me, that's like 90% of mathematics right there. 17.64. Come on. 32. 38.44. We got a 26. We're almost done. 0.04. Really close to the mean, right? 26, only 0.2 away. 29. Oops, sorry. I can do this. And, oh, no. Back. Get out of there. 29. Did we already have a 29? Yeah, 10.24. That's a 2. All right. So there's my x minus mu squareds. Okay, there's my x minus mu squareds. So what I want to do now, I'm going to jump back to this formula here to get my variance. It's sum of x minus mu squareds divided by n. So I'm going to take the sum of x minus mu squareds divided by n. Now, n in this case, again, is my population amount, 10. Okay, so now I just need to figure out what the sum of this column is. So we got 14.44. Again, find joy in the boring. 46.24. 60.84. I got thrown off there. Plus 0.64. Plus 4.84. Plus 10.24. Plus 17.64. 38.44. 0.04, 10.24. We just double check those things. 14.44, 46.24, 60.84, 0.64, 4.84, 10.24, 17, 38.44, 0.04. Okay, we're good. Bingo. 203.6. Okay. 203.6. My total here, my sum was 203.6. Okay. So my variance, divide that by 10, so 20.36. That's my variance. Again, that number, oh my gosh, you just, this is wolf.
I didn't want to stop you, you were on a roll.
Jeez. What's that? Oh, gotcha. No, that's perfectly fine.
I'm so sorry. This is amazing.
No. Did you hear me say find joy in the boring? That's what I was having. See? Hold on, Ben. Okay. Pause for a moment. Let me get him started on a retake. I'll give you guys a topic of discussion. Rhode Island. Neither a road nor an island. Discuss. Stupid.
Why roads like that? What does that mean? Yeah, it's not like that's not like a road you drive on.
You got a calculator?
Yeah, give me my backpack.
Here, I get you one. I got you one.
No, I have one in my backpack. I got one.
Gotcha.
Because of erratically about language shore is a Dutch god. It's France.
I know it.
Yeah.
I know it.
I'm
Boom.
You know that's right. Or like so when we're going, right? You have like the two hands for 8 strikes. Yeah.
You're welcome. Okay, so my variance, jumping back in, is 20.3 cents, right? That's my variance. Again, a number that doesn't really mean a lot to us. But you know what means a lot to us? You know what will mean a greater amount is sigma. So that's sigma squared. So sigma squared is 20.36. So sigma, sorry, my sigmas look a lot like weird sixes. Sorry about that. That's just what it is the square root of 20.36, which is like 4 point something. Square root of this thing, 4.51. There's my standard deviation. Now, what does that mean? That means within 1 standard deviation away from the mean, So the mean was 25.8. Within one standard deviation away from the mean, so 4.5 above and 4.5 below, lies a lot of my data. How much of my data? Oh, just wait. We'll talk about that in great length. 2 standard deviations away from the mean, a bigger percentage of data. So like 9 above and below, 2 standard deviations away. So 9 above and below. So like 34 to 35, all the way down to like 17 lies a lot of my data. Lies actually 100% of my data in this case. But I can talk about it in terms of expanding it rather than just the sample into a entire population. So, but for right now, there's my sample, or sorry, for my population standard deviation and variance. Now, I should have said yes, that was population. So how do I change things if I say sample? Now, I'm not going to make us go ahead and do that all over again. Look at the formula. What is different in the formula? There's only one difference. I'm changing sigma to S. Yeah, that's a difference, I guess. And X bar to X, from mu to X bar. But the only really difference is N minus 1. That's the only main difference to the actual formula. So how do you know when you're going to use the N and when you're going to use the N minus 1? Well, it's all based on the context. It's all based on the context. The context of, is it a population? Is it a sample? Read the problem. Look at the problem. Figure out whether it's a sample or a population. Okay. And again, for a sample standard deviation, we're going to use the little lowercase s. Yeah. S squared is our sample variance. Just new notations there. Lowercase n for the total amount. Right? X bar for your mean. Yeah. We'll use those a lot, so that'll be no problem understanding those notations. Yeah, I'm not going to make us do this all over again, right? How would we know? Well, take a look here. In a study of high school football players that suffered concussions, researchers placed the players into 2 groups. Players that recovered from their concussions in 14 days or less were placed in group 1. Those that took more than 14 days were placed in group 2. The recovery times in days for group 1 are listed below. Find the sample variance and standard deviation of the recovery times. Okay, how would I know that I need to use the N minus 1? Because it's a sample, right? Because it's a sample. I've placed these kids into 2 groups. They're different. They've separated them into 2. This is a sample of the entire group, right? So therefore, I am going to use the formula with the N minus 1. I'm going to use this formula, X minus X bar squared over N minus 1, right? And again, we could go through that whole process of finding the mean and the standard deviation, sigma. I should stop talking and just write this out. Exactly as I had done a second ago, right? You find the mean, you set up all your stuff in a table, you find the mean, you find your variance, or your deviation squared, right? You take your x's minus your means, you square them, you create your new column, add them all up, divide by n minus 1. So in this case, looks like I have my n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I would be dividing by 11, right? Because you divide by n minus 1. So again, forgive me for not making you go through that whole process of doing that all over again. I must have done that. That's probably why this takes so long. Yeah. But I think you kind of get the idea. Now, what's more important to me is how we interpret standard deviation. It's important to be able to find it. It's important to know what it, how to construct it, how to find it. But what's really important is how to interpret it. Standard deviation is a measure of the typical amount an entry deviates away from the mean. The more the entries are spread out, the greater the standard deviation. I've got 3 data sets for you here. All of them have a mean of 5. Each data set has a mean of 5. But what I see here, these are frequency, these are histograms, basically, right? But what I see here is a change in the standard deviation. Okay? I see changes in standard deviation. Look, If I have an S of 0, a standard deviation of 0, that means they are all the same amount. I have 8 entries, they are all 5. Okay, this is a data set that's very nice and evenly spread apart. The standard deviation is 1.2. Look, I've got 5 right in the middle. As I continue outward on either side, it deviates away evenly, right? My standard deviation is 1.2. If I increase my standard deviation, that means my data set is further spread apart. Look, my mean is still 5. But now I've got more toward the far ends of my data. I've got more at 2 and at 8 and less in the middle. That's why my standard deviation is increasing. Right? It's a measurement of how far apart the data is away from the mean, how far it really deviates away from the mean. Take a look here. Estimate the following population standard deviations. The first one here. What do you think the standard deviation would be here without calculating? 0, right? There is no deviation. What about here? Well, my X bar looks like it would be 3, and it's pretty evenly spread apart, right? I would say probably like a 1.5, maybe somewhere in there. Now, here, my X bar was 3, but my deviation was, each of them were 2, right? They've got 3 on either side. Here, my X bar looks like it's right in the middle. Here, it's probably like 4, but it's nice and evenly spread, right? I've got as much below as above, and I see 2 on either side, 2 sets on either side. One's that's 3 units away, 3 units away, 2 units away, 2 units away. Nice and even there, right? This is kind of like this, right? This is kind of represented like this. I would say that's probably a little bit more than this guy, but let's say probably about 2 there, right? Because I can see on either side as much above and below. The standard deviation, it's good to be able to estimate what the standard deviation is without needing to run all the numbers. Like here, standard deviation again is 0 here. Got to be 0. It's not deviating away at all. Standard deviation here, I'd say probably like 1, maybe 1.5, something like that. 1.2, sure, 1.2. Yeah, whatever. It's just an estimation. Yeah. Here, standard deviation. Okay, it looks like the middle of the data is 4. Same thing here. Probably about 2, maybe 3. Let's say 2.5, somewhere in there. Just an estimation. Just an estimation. Okay. All right. Now, where's a good? Let's talk about. Want to get into this yet? Yeah, we got 15 minutes left, right? Okay, the empirical rule. The empirical rule. Now, this is where it starts to get real fun, in my opinion. My version of fun, my nerdy version of fun. Why is standard deviation so important? Why is standard deviation so important, and how can it be used? Just to as we start on this, this empirical rule is this whole chunk of the formula sheet. So it is on the formula sheet. Just fair warning. It's not something that you have to memorize. Back in my day, in my stats class, there were no formula sheets. We had to memorize these things. These numbers have stuck out in my brain. Like when I was starting to teach statistics, I was like, oh yeah, that's right. The 68, 95, 99 rule. That's what's called the empirical rule. Those numbers, I bet you won't even need to work at memorizing. They'll just be in your brain by the time we're done with this. Okay, many types of data follow what we call a bell-shaped curve. A bell-shaped curve, meaning that there is, in real life data, more often than not, if you find a bunch of data, it will come out as what's called a bell shape. Okay, it'll come out as what's called a bell shape. Some people call that a normal curve. Okay, a normal curve. Bell-shaped curve, normal curve. In a bell-shaped curve, 68% of your data fall within 1 standard deviation away from the mean. There's 34% below the mean, 34% above the mean. Okay. In a normal distribution, there is 34% below the mean and 34% above the mean, within 1 standard deviation away from the mean. Okay. As I increase standard deviations away, I say, well, 2 standard deviations away from the mean includes 95% of the data. 95% of the data within 2 standard deviations away from the mean. If I stretch that out all the way to 3 standard deviations away from the mean, we can say, well, I used to call it, back in my day, it was the 68, 95, 99 rule. Our book says the 68, 95, 99.7 rule. That's what they use. Okay, sure. But basically, it's saying that within 3 standard deviations away from the mean, almost all of the data should be within that range, plus or minus 3 standard deviations away from the mean. This is what's called, again, the 68, 95, 99.7 rule. For data with symmetric bell-shaped distributions, normal curves, the standard deviation has the following characteristics. First thing, about 68% of the data lie within 1 standard deviation away from the mean, above or below, right? 34% above, 34% below, within 1 standard deviation away from the mean. 2 standard deviations away from the mean get 95% of the data included, and 3 standard deviations away from the mean get 99.7% of the data included. So within 3 standard deviations away from the mean, you should have darn near all of your data. Okay, if this thing is bell-shaped, and that's going to be a caveat that we have to remember, like, the entire year. I will talk again and again and again about, well, you assume that this is a normally distributed set. Okay, the assumption that this is normally distributed. Okay, that is always a big assumption, something that sometimes you have to prove. Okay, take a look here. How do we use it? Well, a survey found that the sample mean height for adult males was 70 inches. This was a survey, right? This was a sample. The survey found that the sample mean height for adult males was 70 inches, with a sample standard deviation of 3 inches. Could we have calculated that if I had been given the sample? Yeah, we know how to calculate standard deviation. We know how to calculate mean. I could have given you like 10 people. I could have given you the raw data and you could figure this out. So a survey found that the sample mean of height for adult males was 70 inches, X bar, 70 inches, with a sample standard deviation, lowercase s, of 3 inches. Estimate the percentage of men that fall between 67 and 76 inches, assuming a bell-shaped distribution. That is a big assumption, right? We are assuming that all males have a normally distributed height. Assuming that. Now, so take a look here. If I know that this is normally distributed, we can draw this bell-shaped curve. What number is exactly in the middle of this bell-shaped curve? 70. There's our X bar. I know that based on the empirical rule, the 68, 95, 99.7 rule, that within 1 standard deviation away from the mean, here and here, 68% of my data lie. What are those numbers in this case? What's 1 standard deviation above? 73. What's 1 standard deviation below? 67. I know 68% of my data fall right there. I know that 95% of my data fall between 64 and 76, right? Because this is 1 standard deviation away from the mean. This is 2 standard deviations away from the mean, right? Okay, now look, I want to know, fancy highlighter here, I want to know the percentage of my data that fall between 67 and 76. I want to know how many people are included in this shaded region here. That's what I want to know. Okay, is it symmetrical? No. But I can still find the percentage of people that would fall between there. Let me ask you this. If I... Oh, no, let me get a pen, please. Let me get a pen. If I were to only look at this green piece in here, what percentage of data fall in there? 68%. So I know it's got to be at least 68%. It's got to be this 68% plus this chunk in here, right? So let's figure out what that chunk is, right? Let's figure out what that chunk is. Well, the best way to do that, in my opinion, would be to say, well, this is, well, is there a better way? Actually, you know what? There might be a better way than that. Think about this. I'm going to try to rearrange my thought process here. Can I calculate this pretty easily? How much was 2 standard deviations away? 95, right? Isn't that half? Isn't this purple half of the 95? Right? This purple piece is half of the 95. So what is half of 95? That is 47.5. So I know this is, I'll put it in here, 47.5% of my data fall right in there, right? So now I just need to add on this yellow piece. So what is that yellow piece? Well, this is 47.5. Wasn't this half of my 1 standard deviation? Isn't 67 to 73 68% of my data? So what's the left half of that? 34%. So this yellow piece in here is 34%. So to go from 67 all the way up to 76, I would take 47.5 plus my 34. So 0.5, carry the 1. 81.5% of my data fall between 67 and 76. Assuming that this distribution is Dow-shaped. Assumptions. Okay, we will finish that tomorrow.